is not correct. Okay, no problem. So good morning, everyone. I'm Giuseppe from Politecnico ABC department. I'm presenting this work we made with my supervisor Matteo Ruta and Gabriele Masera. Well, I will start talking about decarbonization. That refers to the process of transitioning away from fossil fuels, energy sources, and reducing carbon emission to mitigate climate change. And this is something we all know and we have to face. But in our pursuit to decarbonization for building industry, it's crucial to understand the significant how we address this decarbonization. And we can work on two sides, both embodied carbon and operational carbon. When we work on embodied carbon, is fundamental, is the carbon stored in materials, etc. But when we take a look at cities and buildings in the long run, we have to focus also, and in my case, mostly on operational carbon. And in this case, we can effectively tackle the largest source of emission in the building sector, and addressing operational carbon offers a more immediate impact on reducing greenhouse gas emissions. And considering the decarbonization targets across Europe and the most recent implication also in terms of finance due to the new climate law and the European taxonomy, we are kind of forced at all levels, from global to private level, to use and to enhance the use of data for building performance simulation to abstract real-world evidence and support informed decision to assess and reduce the environmental impact of buildings and meet the strict requirement related to performance objectives. Well, so we are in the middle of a market pull and a legislative push, and this is our old building sector, and it is a unique interplay between these two factors, and is like the first time in a while that we are facing these issues. And the key point is that works both on our projects and our cities. So we are talking about cities because the synergy between market forces and regulatory measures is crucial for accelerating the piece of decarbonization and achieving our goals. But why urban energy? When we are discussing decarbonization in the building sector, it is essential to shift our focus from individual buildings to energy consumption at the city scale. While optimizing building level efficiency is crucial, obviously, we also must understand the energy consumption at a larger scale because it offers a significant advantages and unlocks broader opportunities for sustainable development, such as you see written there, we can go beyond the individual buildings and have a more holistic understanding of the urban energy landscape, because we have to understand that cities are complex systems with interconnected structures, etc. So we are focusing on data-informed urban energy analysis. And why? Urban energy analysis are important for analyzing fast analysis of building clusters, such as new developments in cities. We see in all cities around the world nowadays, due also to increase in population, for example. We can use it for design exploration, urban volume optimization, and district heating cooling feasibility, for example. And all these wonderful things, now we will focus on design exploration mainly, lead us to a problem. Urban analysis requires lots of data, so they are computational intensive, and data are often difficult to access due to data privacy, collection methods, etc. So what if there are not enough data available? This is our approach. We try to define, to use an existing data set, and we use this correlation between input and outputs in the early design stage for the cooling load forecasting. So we used a machine learning-based tool. We evaluated it using the squared error value. And then, simulating a real-world scenario, we removed 60% of the dataset, regenerated it using a GAN, and re-performed the same machine learning model to evaluate if it's feasible or not. It's like a proof of concept, we can say. So the training dataset, the original one, is made of these 12 building shapes. Each building shape is made of 18 modules, all with the same volume. So they have all the same volume. We made 64, they have 64 variation, is an existing dataset. So we have a total of 768 instances with 8 input and 1 output. The output is the cooling load, as we said before. And inputs are this one. So we have the relative compactness, surface, wall, roof area, height, orientation, glazing. So as you can see, this is the most important part. They are all geometrical inputs for one output mostly related to energy. So we generated this dataset. The GAN, as you may already know, is the Generative Adversarial Network. And we used it we removed 500 on 768 instances and regenerated the same number. You can see the distribution and the standard deviation is kind of good. And here we can see the results. So the red one is the real data, and the blue one is the artificial one, the generated one. And some of this data, you can see they are continuous, like the orientation or the wall area. We can have all the values between one number and another. And others, like the orientation and the glazing, orientation I told twice, but orientation is non-continuous, sorry. The orientation and the glazing area, they are discrete, and they are the line below. So this is the new distribution of data. I'm sorry for that, but they are the opposite. So the red one are the real one, and the blue one are the artificial one. I'm sorry for that. And we can see there is the new distribution of our input values. So we need now to prove the accuracy of the model trained, and we used, as I said before, both before generating dataset and after that, a machine learning tool. We use a cut boost regressor, for example, in this case. We can totally change it, we can compare it to others, but in this case, it's we are checking only the feasibility of this study. So these are the outputs. And as we can see, the first graph is before the data integration with the artificial network. And we have a super precise analysis and simulation. We have the possibility to analyze 768 buildings with load forecasting with an accuracy of more than 90%, more than 95%, in less than 12 minutes. Below, you can see the huge difference and the drop we have in accuracy with the GAN-generated dataset. But here is the main point. So we have no accuracy of the model in time, so we cannot use it for combined energy load forecasting. And we cannot use it for these urban scenarios. But as you see before, the peak loads and the average is correct. So if we consider this at an early stage design at a urban scale, we can use it right now. Obviously, we need further work, but we can use it for the peak analysis, load forecasting, and it's a super limited time required. So it's a totally good thing for the designers. Next steps are the dataset normalization. We will work on scaling, and we will try to compare different machine learning models to see if something can be improved, if these results can be improved also in the second stage. That's it. This is me and my contacts. Thank you.